Now, the question is there are 4 control variables. Now, using these 4 control variables, what should we do? So, what should be the considerations that influence the choice of the values of these 4 control variables? So, let us see how we can use this. So, we have 4 control variables at our disposal. Okay. So, the considerations which influence the selection of control. That means I want to select the values of the 4 control variables. So, what are the considerations which will help me in choosing the values of these control variables? Yeah, any guess? What should be? Any idea based on your previous knowledge? Four control variables are there. How best can we use this? Maximizing, see, power flow is always decided by load. Say what decides power flow? Say if some load is connected, okay. Now, depending on what is the requirement of the load, we send some power. So, we may not want to maximize the power flow. Okay. Sometimes, of course, we may want to regulate the power flow, control the amount of power flow, but not always maximize. If it is not required, why do you want to maximize? Say under light load conditions, we may not want so much power to be transferred at all. So, there is no need to always maximize power flow. Any other consideration that may help us in deciding the values of the control variables? Power factor, yes, power factor. Now, power factor should be always close to unity. So, it should be as high as possible. Okay, that is one thing. Okay, let me note that. Maintaining power factor. Now, when I say power factor is defined only on the AC side, and there are 2 AC sides here, one for the rectifier, one for inverter. Okay. So, maintaining power factor at rectifier and inverter sides. Now, at each of these locations of rectifier inverter, I am talking about the AC side only. Please note, power factor is always defined for the AC side. There is no definition of power factor on the DC side. At rectifier and inverter sides as high as possible. Yeah, any other consideration? Now, okay, just now in the context of maximizing power, I just mentioned that we may want to regulate power. Instead of maximizing, we want to regulate the amount of power. Say otherwise, if you do not regulate, say in an AC system which is unregulated, the amount of power is decided by Kirchhoff's laws, Kirchhoff's current law and Kirchhoff's voltage law. So, many times we want to have control over the amount of power flow. So, here it is possible because there is a thyristor at both the rectifier side and inverter side, there is a possibility of regulating the amount of power flow. So, if I control the power, so the control of power, now I mean what I mean here is the power that is actually transferred through the DC line. So, if I want to control power, that means if I want to change the amount of power, what I should do? Power is equal to the voltage into current. On the DC side, there is just voltage into current gives power, average voltage into average current gives power. So, I can change either voltage to change power, or I can change current to change power, or I can change both. Now, which is desirable? Suppose I want to change power, okay. Suppose I want to change, power is at some value now, I want to change it. Now, for doing that, will I change voltage or will I change current? I will change current. Now, is most of the, I mean, we will try to see that current is always minimized because we want to reduce losses, okay. So, if current has to be minimized means voltage has to be always at value as high as possible. So, almost at the rated value. So, for control of power, what we do is keep voltage at rated value and change current. So, keeping voltage at the rated value, or see, rated value is the maximum possible value. So, changing current will actually result in minimization of loss, and keeping the voltage rated value is actually equivalent to minimization of loss. So, it is essentially maintaining the DC voltage near rated value. So, it is what I am trying to say is maintain DC voltage at rated value. So, why we try to maintain a DC voltage at rated value? Say the DC voltage is dependent on the AC voltage. Now, due to changing conditions on the AC system, the AC voltage itself may vary. So, even in spite of variation in the AC voltage, keep the DC voltage at the rated value, that is the point. So, using some of the control variables, you try to keep the DC voltage constant at the rated value in spite of variations in the AC system voltage. So, variations in the AC system happen because there are always changes in the system. See, the main change that is happening is always the amount of load that gets connected to the system. So, there is a daily variation. I mean, during daytime, the amount of load that gets connected is different from the load that gets connected after it is dark, and after it is midnight it is different. So, there is a curve, a daily curve, and there is also a weekly curve. Weekdays the curve is different, weekend the daily curve is different, and there is a seasonal curve. Summer it is different, winter it is different. So, I mean the load is something which is not constant, due to which the system conditions are different, and due to which the voltage at the AC system bus itself can change slightly. Okay. So, in spite of all these changes, we want to maintain the DC voltage at the rated value. Yeah, that is one consideration. Any other consideration? Any other consideration? You look at the 4 control variables. So, looking at least the variables TR, TI, alpha or gamma I, you may get some hint. What is gamma I? Huh? Commutation margin angle for normal operation. Now, we need to control this because we do not want the commutation failure to happen. See, what is commutation failure? The voltage across an outgoing valve becomes positive before it is supposed to become positive. Then it will turn on even without gate pulse. That should not happen. That is called commutation failure if it happens. Okay. So, prevention of commutation failure is one of the considerations. So, if I want to prevent commutation failure, it means that I should have a minimum value of what? Here, I mean, among the 4 control variables, the minimum I should have gamma I to be greater than a certain threshold. Otherwise, it will I mean result in failure of commutation. Yeah. Any other consideration? One consideration that is very important whenever we have a power electronic device is prevention of large fluctuations in the direct current, the DC side current. So, this can be due to variations in the AC system voltage. Okay. Now, among these considerations, power factor is something I mean which will result in many other advantages if it is maintained at a high value. So, say why should we read? Okay, reasons for it's I mean of course from the previous knowledge that you have, I mean you are all familiar with the advantages of having a high power factor. Okay, but still for sake of completeness, let me say a few more things about why we should maintain high power factor. Now, that is because I want to specify the reasons which are specific to this particular circuit or system that we have, the DC transmission system. So, one reason for high power factor is, say, if you look at any equipment, say a converter, it has a voltage rating, current rating and a volt ampere rating, and it also has a power rating. Now, for a given voltage rating or a given current rating, if the power factor is very high, the active power that can be transferred through the converter can be maximized. Okay. So, that is one reason. So, to keep the rated power, see, when I say rated power, I am not talking about the apparent power, the rated active power. So, to keep the rated active power of converter as high as possible, for a given voltage and current rating, for given voltage and current ratings. Now, this power factor is defined on the AC side. So, the AC side means the AC side we have the AC system. So, I mean, is there any advantage of having a high power factor? See, AC system can be always represented by a voltage source or a voltage source in series with an impedance. Okay. Now, if I represent the AC system as a voltage source in series with an impedance, which is essentially inductive, then if there is a large power factor, then there is a large drop in this equivalent inductance impedance, due to which the voltage that I get may vary depending on the amount of the current. So, as the amount of the current varies, then the variation in the voltage is also present. So, there is essentially a large drop in the equivalent impedance that is representing the AC system. So, if I mean that will cause what? I mean, large drop means it will cause more losses in the system, not only reactive power losses, reactive power loss will also cause active power loss, because due to reactive power I need to draw large current will result in losses. See, that is one of the major reasons of avoiding reactive power flow. So, if you allow reactive power flow, it is actually allowing more current, which will result in more loss. Okay. So, to minimize loss in the AC system, then so when I say I want to keep the power factor as high as possible, what exactly is the problem? I mean, if I do not keep as high as possible, though we do not talk about lagging or leading power factor when it comes to presence of harmonics, if I just take fundamental frequency, is the power factor lagging or leading in this case? Forget the harmonics for the time being. What is happening to the power factor? It is lagging or leading? See, why I am neglecting fundamentals is, we will see that shortly we will design some filters which will actually try to minimize the harmonics, and some of the harmonics can be in fact eliminated almost. So, essentially the current that is drawn from the AC system is almost sinusoidal. Okay. So, essentially we are having only fundamental current or fundamental voltage and current at the AC side in the presence of filters. Okay. So, in that case we can talk about lagging power factor and leading power factor. So, till now we can't talk about, because we have not talked about it, because we have not still considered filters. So, with filters we can ignore the harmonics and say there is only fundamental, then we can talk about our lagging or leading. So, the question is whether there is a lagging power factor or a leading power factor. Essentially it is asking whether I draw reactive power from the AC system or supply reactive power to the AC system. In other words, if you look at the individual currents, see, the currents are lagging the voltage or currents are leading the voltage? Lagging the voltage. So, that means reactive power is drawn. So, if more reactive power is drawn, I have to somehow make arrangements for supplying that. So, if the network is not able to supply, network may not be able to supply because I mean at some point the loss becomes large, our network itself has a limitation. So, what we do is we locally provide a reactive power source. That means we supply reactive power using capacitor is one possible source. Okay. So, in order, so if I want to provide locally, there is a cost involved. I mean, if I want to provide an additional capacitor, there is a cost involved. So, I want to in fact minimize the cost of the reactive power source as well. That is why we want to keep a high value of power factor to minimize cost of reactive power source to the converter. Okay. Yeah, any other? Yeah, there is one more advantage of maintaining high power factor, which is very specific to this line commutated converter. Maybe you would have not noticed this. If there is some relationship between power factor and alpha, if you take the simplest line commutated converter, ignoring say the inductance for the timing, for the sake of simplifying the explanation. Now, is there a relationship between the power factor and alpha? They are equal. I mean, the cos of alpha is nothing but power factor. There is one more thing. If you look at the dV by dt, the change of voltage, the voltage jumps, they are proportional to what? They are dependent on alpha. But in the expression, what do you see? You recall? Just take the simplest case. Without inductance, there are 3 voltage jumps. So, these voltage jumps are dependent on alpha. But what is the expression? Do you recall? You may not remember the exact expression, but how it is dependent? Sin alpha. Now, I want to, I mean, should these values be, voltage jumps be smaller or larger? As small as possible, so that dV by dt stress is reduced. So, that means alpha should be, no, for rectifier it should be close to 0, for inverter it should be close to 180, only then it will be small. Okay. So, when alpha is close to 0 or 180, what is happening to power factor? Large. So, there is a relationship between power factor and dV by dt stress. So, maintaining high power factor will also result in reducing dV by dt stress. Now, it is easy to explain in the case of the simplest one without inductor. Now, even with inductor, in addition to alpha, there is a U also. Okay. Now, it is difficult to say looking at the expressions, but one can verify it. So, take a practical converter, assume some value of alpha, find U and see what happens. One can show that, one can show, it is not possible to prove that in theory, but one can show in practice by calculations that maintaining high power factor is equivalent to reducing dV by dt stress, even in the practical case of inductor being present on the AC side. Okay. So, that is something not very obvious. So, okay, let me write this as to reduce dV by dt stress in the valves, thyristor valves. So, these are the considerations used for deciding the values of the control variables. Now, which consideration is used for deciding which control variable is something is said to be answered. Now, a few things are very obvious. If I want one of the considerations, prevention of commutation failure to be used. Now, to prevent commutation failure, what should I do? I have to regulate gamma I. So, the control variable gamma I is regulated in order to ensure that commutation failure is prevented. Then if I want to satisfy the second consideration, okay, let me come to a much easier case. Last one, prevention of large fluctuations. What do we do? So, which control variable can be used for prevention of large fluctuation? See, the third one is very obvious. The third consideration, main prevention of commutation failure, is equivalent to regulating gamma I. That is one of the control variables. See, the 4 control variables are here. Just now I mentioned TR, TI, alpha R, gamma I. So, gamma I can be used for the third consideration, that is prevention of commutation failure. What about preventing large fluctuation in the direct current? That means essentially trying to regulate the current in the DC line. So, alpha R. Now, it should be obvious because TR and TI are slow controls. TR and TI are slow controls. The only fast controls are alpha R and gamma I. Gamma I is used for the inverter commutation failure. So, by now you should be clear that commutation failure is not an issue for rectifier. It is an issue only for inverter. That is why we are not considered gamma R. We are saying gamma I, that is for the inverter. So, alpha R is the only remaining fast control variable. So, that can be used for controlling the current, that is the fourth consideration. Then there are TR and TI. So, these two are used for the other two considerations. One is maintaining a power factor, the other one is maintaining the DC voltage. So, what we do is we use this TI, the tap on the inverter side is actually used to ensure that the voltage is regulated on the DC side. So, that is a slow control variable. So, that is not a very stringent requirement. Suppose for a few seconds the DC voltage is not maintained at the rated value, the heaven will not fall, but there is a problem if the current fluctuation is not avoided. Okay. So, there are a few things which are not critical. So, maintaining DC voltage is not so critical. If it takes a few seconds to control DC voltage, it is still okay. So, we can use TI. Now, TR is actually used to maintain power factor. So, we maintain power factor by keeping alpha R as low as possible. Okay. So, but one thing is alpha R as low as possible means one can say that keep it at, what is the lowest possible value of alpha R? 0. But we do not do that because if we keep alpha R at 0, now due to some reason, suppose a large load is suddenly connected on the AC system, the AC system voltage will fall. Now, we can't increase the DC side voltage because alpha R is already at 0. To leave some margin, we keep alpha R at a value between 10 and 15 degrees. So, even if there is a large reduction in the AC side voltage, we can still increase the DC side voltage by reducing alpha. So, we leave some margin. Okay. So, that is how it is controlled. So, let me summarize. So, gamma I is used for preventing commutation failure in the inverter. So, that is the first control variable. So, this type of control is known as constant. So, what is there is a name given for gamma, you recall? Extinction angle. So, constant extinction angle. Abbreviated as CEA, constant extinction angle control, is employed at inverter. So, the acceptable value of gamma I is 15 degrees for, now please note the acceptable values of gamma I is nothing but acceptable value of commutation margin angle, because normal operation is considered. So, it is 15 hertz and it is dependent on frequency. Please note it is dependent on frequency. So, 15 degrees for 50 hertz, and if it is 60 hertz, if it is 60 hertz, 40, 20. So, what is it for 60 hertz? Now, you go back to the definition of commutation margin angle. See, commutation margin angle has nothing to do with angle. It has something to do with time. The time taken or the time required for the voltage to again become positive. It is only the time. So, in terms of angle, it depends on frequency, that is all. It is not obvious. See, 15 degree for 50 hertz and 18 degree, I mean has some, okay, 15 degree for, okay, let me say 15 degree for 50 hertz means what is the time? What is the time? What is the time in 15 by now, can I write this in terms of degrees? See, I have said 15 degree for 100 hertz. Okay, if I take one cycle, it is 360 degrees. One cycle is 360 degrees. Okay, so I want this in time. So, for 50 hertz, the period is 20 milliseconds. So, 20 milliseconds corresponds to how many degrees? 360 degrees. So, what is this 15 degree equivalent to in terms of time? 15 by 360 into 20 milliseconds. Okay. So, I want the same time for 60 hertz, that is all. So, for 60 hertz also I should find the angle so that it has the same time. So, actually same time means 15 by 360 into 20 milliseconds. But the thing is, now the period is different. Period is not 20 milliseconds, it is 16.66 milliseconds. Okay. And angle will also be different. So, what should be the angle? 18. Now, that is because this is equal to 18 by 360 into 16 2 by 3 milliseconds. Is this, I presume this is a straightforward calculation. If not, let me know. If it is complicated, let me know. Okay. So, how do I get 20 milliseconds? Okay, let me give some more steps. How do I get 20 millisecond? It is 20 milliseconds is 1 by 50 seconds, 1 by 50 seconds. So, here 1 by 60 seconds I have to take. Okay. So, what I am trying to say here is it is 15 by 360 into 1 by 50 seconds. So, here also I want the same thing. So, this is also I want the same thing, 15 by 360 into 1 by 50 seconds. So, is this equal to 18 by 360 into 1 by 60 seconds? Are these two equal? This is this equation correct? That's what I am saying. So it is 18. So this is 18. So that's how we control gamma. So there are 3 more control variables. So I'll summarize them in the next class. Okay. So and still, I mean, a few more things have to be mentioned in as far as control is concerned. We look at that in the next class. I'll stop here.